This module is devoted to adiabatic processes. As a reversible adiabatic process, we understand a reversible change of state of a closed system with adiabatic boundaries. Here, closed indicates a system that doesn't exchange matter with the surroundings. Reversible means that the system is always in equilibrium with the surroundings, and adiabatic means that there is no heat exchange with the surroundings. According to the first law, the internal energy in such a system changes solely due to work. We will again only consider compression or expansion work done on or by the system and neglect all other types of work. On the other hand, the change in internal energy is also equal to the heat capacity at constant volume CV multiplied by the change in temperature dT. What happens if one performs an adiabatic compression? Compression means that the volume decreases, dV is negative, internal energy increases, du is positive, and temperature increases, dT is positive. So, adiabatic compression leads to an increase in the system's temperature because there is no heat release. Similarly, during an adiabatic expansion, the volume increases, internal energy and temperature decrease because there is no heat flow into the system to maintain its temperature. When examining reversible adiabatic processes involving ideal gases, some interesting mathematical relationships emerge. With some deviations that we won't consider here, we arrive at equations that describe the connections between different pairs of state functions for an ideal gas undergoing a reversible adiabatic process. Just like previously discussed isobaric, isochoric, and isothermal gas processes, reversible adiabatic process can be understood and employed in a similar fashion. The graphical representation of these equations is referred to as adiabatic curves or adiabats of ideal gas, much like isobars, isochors, and isotherms. Central to these equations is a parameter known as the adiabatic exponent, denoted as gamma. It represents the ratio of the molar heat capacity at constant pressure to the molar heat capacity at constant volume. Given that for an ideal gas, the molar heat capacity at constant pressure always exceeds the molar heat capacity at constant volume, gamma is always greater than 1. And here are the equations. The pressure multiplied by the volume raised to the power of gamma is equal to a constant. The temperature multiplied by the volume raised to the power of gamma minus 1 is equal to a constant. The temperature raised to the power of gamma multiplied by the pressure raised to the power of 1 minus gamma is equal to a constant. The temperature multiplied by the pressure raised to the power of 1 minus gamma divided by gamma is equal to a constant.